I'm going to talk about G-Commutative Monoids. And I was told to give an introductory talk. Actually, I was told this on Christmas Eve when I guess Santa got my letter for feedback about what to do. And so I want to talk sort of about a general framework for how you can think about a lot of these. And then on Friday, when I talk again and we're all exhausted, I'm going to say a bunch of things that are kind of weird that I've noticed since first trying to think about these things. Full disclosure, I'm a little jet lagged. So I also am not really sure where today's talk is going to go, so it's a little bit of an adventure for all of us. But let me start with sort of a Siegel approach to ordinary commutative monoids. So Siegel's approach. And so the idea here is, let's say that I just have an object in sets. Then, given any object in set, I can write down two functors. I get a functor from finite sets and isos into set. And this takes a finite set T to just take the t-fold Cartesian power of my object M. And then this functor actually has a natural extension to a functor from finite sets A into set, where I again take T to the t-fold Cartesian power of M. And the Cartesian powers are contrarily functorial in the thing that I'm using to index my power. And so what sort of Siegel noticed is that I can rewrite the property of being a commutative monoid by instead taking this functor from fin iso into set and building a covariant version. So if I start with just my multiplication, well, this is a map from M cross M back to M. And I can encode all of the properties like commutativity, like associativity, diagrammatically. And remember, this is just M crossed with itself to the 2-point set, going back to M crossed with itself to the 1-point set. And so there's my covariant functoriality. But if I include, say, the automorphism, the non-trivial automorphism of the 2-point set, where I swapped the two factors, then my multiplication's commutative is the same statement as this diagram commutes. And my multiplication's associative is the same statement as this diagram, where I crossed with itself 3 times. I have 2 ways to get down to crossing with itself twice, and then I map back out to M. That this, I'd say, commutes, that all the ways that I get from here down to here give me the same thing. And again, I can package this as saying, here I had my functor, in this case from the 2-point set to the 1-point set, and there's a unique such functor. And so I'm really just lifting the diagram that I had in finite sets, where I swapped the 2 points, and so I should have given them different names. And then here I had 3 points, and there's a unique map here. And so I'm asking to lift this whole picture. And then this is all I actually needed. So the data that I've written down here was an extension. So this having a multiplication, that multiplication being associative and commutative, gave me an extension where I took finite sets and surjections and extended and sent this into set, where I was again extending finite sets and isomorphisms. So this is my given thing, and this extension is the same data as a non-unital commutative monoid structure. On M. So to get the unital part is also essentially the difference between talking about finite sets and epimorphisms and all maps of finite sets. And so here I'm going to ask for that last piece. Well, if I took M to the empty set, that's just a point. And so to give myself a unit is exactly the condition that I gave myself a map from this back to M that was picking out the element that was my unit, and then the extensions or the diagrams that encode it being the unit are just recording for me things like if I did point and I take the disjoint union of that with the empty set, well, that didn't do anything, but I could have included this into point disjoint union point, as I guess I wrote it as the second factor, and then I multiply. This composite is naturally isomorphic to just the, well, it's a natural isomorphism. And so that's recording for me when I took this whole thing and put it as the exponents for the M, that's saying that the condition that looked like point cross M going to M cross M, going to M, where point went in as the unit, was exactly recording for me just the natural projection onto the M. That's that multiplying with the unit is the identity. And so this additional data told me that if I take my finite sets and isomorphisms, again, this functor that went into set, that was determined by M, so we'll just write it as M, then I can extend this over all finite set maps. And this extension is exactly the data of a commutative monoid structure on M. And so there's a couple of places that I can go here. The first of which is I can say, well, now I have two kinds of functors in. I have a functor from thin up into M, and then I also have a functor from thin into set, and so I can hybridize these, and this gives me sort of instead I might call it a Lindner approach. So I can combine these. These two functors, I get a map from the correspondence category. So I can define the category script A to have objects, again, finite sets. And then the morphisms between two finite sets are going to be isomorphism classes of correspondences. So sometimes also called spans. And here the composition of such a correspondence is given by pullback. So here's my composite of the two spans. Now the correspondence category has some really nice properties. And one of which is that in this category, the disjoint union of finite sets is the categorical product. And if you haven't seen this, then I'll suggest that this is an exercise. I'll describe to you the projection maps. So here I have S disjoint union T, and I need a map to either S or to T, so I need a correspondence. Well, there's a really easy to write down map from S to S disjoint union T. If this were a calculus class, I'd say, what's your favorite map from S to S disjoint union T? And then I'd be pleasantly surprised by the variety of answers I get. So what's your favorite map from S to S disjoint union T? Thank you. Yes. Even more pleasantly surprised to only get one answer. So S includes into S disjoint union T, and then it also equals itself. And so I've written down a correspondence. And the same thing, I just character swap S and T, and that gives me the other. So the nice feature here is that, that we can consider functors. So I'm going to say that a functor from A into set is product preserving if two things hold. First, I want M. I want M of the empty set to be a point, and I want that if I take M of the disjoint union of two things, so the categorical product, then there are maps from just functoriality to M of the two factors, so that gave me a map from M of the categorical product to the categorical product of the values of M on the two pieces, and I want this to always be an isomorphism. And now, given product-preserving functors, I can actually describe another way to talk about a commutative monoid. So, if M is product-preserving, then I have, for any T, well, I can look at M of T disjoint union T, and there's a fold map from T disjoint union T back to T. So I can just take M of the fold. And the product preserving part said that this was isomorphic to M of T Cartesian square. And so here is my multiplication back. And the axioms, and this is a kind of fun exercise actually to work through, that just knowing these product-preserving conditions and knowing that my composition comes from pullback, then you can work through and see that, in fact, this is actually a nice commutative monoid. All the stuff I talked about here goes through mutatis mutandis. And so I get that the assignment from product-preserving functors down to commutative monoids, which just took a product-preserving functor and evaluated it at the one-point set, that this is actually an equivalence of categories. So I can see, I can rebuild anything. Okay, so this is the sort of setup that I want to do, and now I want to start folding in equivariance. So I don't know. For some reason, I'm going to use baking metaphors, at least for now. Probably because when I woke up at midnight, never mind. Okay, so now I'm going to be working in G spaces, and I want to sort of build up the same kind of idea. And I want to now also think about the same sorts of things. I'm taking a very naturally defined functor from finite sets and isomorphisms, and then I'll start to enrich this. And the enrichment that I'm going to use is going to be governed by exactly what I see in the equivariant story. So I'll try to keep it as canonical as possible, but in sort of a religious sense. It's just handed down to me from the mathematics itself. So let's start with the category of G spaces. And I think I should probably say, I actually mean sort of the infinity category of G spaces. And so for the nice model of this that I'm going to take, I'm going to use Elmendorf's theorem. So given a G space, I can write down two kinds of things. I can write down a functor on the orbit category into spaces. And I'm not sure I left myself space. So maybe as a reminder, the orbit category here is just the full subcategory of G spaces spanned by the orbits G mod H as H ranges over the subgroups. I'm going to be, I know I'm going to get this question. I'm actually today only going to be talking about finite groups. So a lot of this I don't know how to do in the compact Lie case, and I'd love to understand exactly how to make it work. And it turns out there are groups that are neither finite nor compact Lie, like Z, and I don't accept them. So
very finite groups.
and there are profinite groups. So, okay. So, you completely derailed me with that comment. All right. So here I have this full subcategory spanned by just the orbits, and my functor here took G space to the functor on this that took G mod H to just maps of G spaces from G mod H into X. And so one of the first things that you see when working with this is that maps out of G mod H, well, the G maps out of that is something that I can understand. This is naturally isomorphic to just H equivariant maps out of a point into the restriction to H of X. And an equivariant map out of a point, well, a point has a trivial action, and equivariance always, at worst, grows the stabilizers. So this is just the H fixed points of X. And so I can think about this as recording for me the diagram that in actual spaces with a group action, as I vary the subgroups, the various fixed points include into each other. It's sort of a kind of stratified space. And the strata are given by the fixed points as I range over the subgroups. What this remembers for me and encodes pretty nicely is that I also have the automorphisms of G mod H acting on on the value at G mod H. So I'm going to call this a coefficient system. This will be a coefficient system of spaces. And then if I had other target categories, I would have coefficient systems there too. So I also have functors from the orbit category into set. And the other I'll actually spend more time considering are functors from the orbit category into, say, abelian groups or commutative monoids. And these are what people have traditionally called coefficient systems. But I want to sort of put them all on equal footing. And I have functors that are compatible between these, so I can take pi 0, and pi 0 actually gives me a functor from the coefficient systems of spaces. I guess this is the appointed spaces into coefficient systems of sets. And here's where I want to work, and I want to now play the same game. While I'm erasing, any questions? Time's up. Okay. I said time's up, Julie. Is that high enough? Okay. Alrighty. So now I have a little bit more since I'm working in these diagram categories. I have an inclusion of the orbit category for H into the orbit category for G. And basically what it does is it's induction. So I take an orbit H mod K and I send it to G mod K. So I said inclusion, but this isn't a fully faithful embedding. This is a faithful embedding inside. But in fact, it's important that it not be full. There's sort of two ways that I can do this. And so I want to stress, though, that this is not full. And I don't sort of close it up under the full piece. And so here's the prototypical example. Let me look at the orbit category for CP. Well, when I do the orbit category for CP, there are two types of orbits. There's CP mod E, the trivial group, and there's CP mod CP. And there's a unique map from CP mod E to CP mod CP, and right multiplication by elements of the group gives me an action of CP on this. Well, really, if I'm being extra pedantic, I should call this CP op, because I'm doing the right multiplication of the group on itself. I mean, it doesn't matter, groups are canonically isomorphic to their opposite, but yeah. Now if I look at I mean, I guess I could look at the subgroup CP, but then it is a nice fully faithful inclusion because it's the identity. So let me take the other subgroup, the identity, and if I look at the orbit category for the trivial subgroup, well, that's the trivial subgroup mod itself. This is the 1.1 map category. And the map here is take this to that point and just remember the identity automorphism. But associated to this, I can build a bunch of compatible functors. So precomposing with this, I get a restriction map. IH upper star, which goes from coefficient systems for G to coefficient systems for H. And if my target category, I'm actually going to be super agnostic as to what kinds of coefficient systems, so coefficient systems of somethings, and provided my something has like limits and colimits, then these have both adjoints. So this has a left adjoint, which traditionally would be called induction, and a right adjoint. Which traditionally is called co-induction. The left adjoint, these have a different description that's a little more intrinsic. And I could have put this back up here. So since I already talked about product-preserving functors, if I take instead of the orbit category, I take all finite G sets, then finite G sets is the coproduct completion, or the finite coproduct completion of the orbit category. So I get fin G is the finite coprod completion of the orbit category. And so what I get from this is that coefficient systems on G are actually the same thing as product-preserving functors from fin G op into whatever thing I have that has products. So this description's kind of nice. First, it fits in the framework that I'm sort of moving towards here, but then second, it gives me really clean formulas for the restriction and for co-induction. So with this, the restriction to H of some G coefficient system M, well, when I evaluate it on a finite H set T, this is just take M and induce up T. Whereas co-induction from H to G of M evaluated on a G set T is just restrict T to H. And these are nice. Now, I'd planned to make a joke at this point where, Leonard revealed that he'd worked with me as a postdoc, and even in doing so, he didn't pick up sort of a love of formulae. So the joke here was going to be, even though Leonard worked with me as a postdoc, I didn't sort of pick up his distaste for concrete formulae. But I'm going to avoid it because I decided in the end that joke was boring. So instead, these are the two things that I'm going to look at. Now, you'll notice I didn't write down a formula for induction. And induction, it doesn't have, in this case, a nice clean formula. If you're used to Mackey functors, maybe you've never thought about coefficient systems because why would you? If you're used to Mackey functors, then I would say, oh, well, this is also a formula for induction. And in some sense, the hallmark of Mackey functors is that I have a restriction functor and it has both adjoints, and those two adjoints agree. It's the same thing that I see in the hallmark of genuine equivariant homotopy theory, as opposed to the other types of equivariant homotopy theory, which often get kind of dismissive names like naive. that the real thing is, do I have the same property? Is induction the same as co-induction? In this unstable, not genuine, counterfeit version of equivariant homotopy, I have a huge difference between these. And so let me give you the example for CP. Then a general CP coefficient system, well, I had to give you the value at CP mod CP. I had to give you the value at CP mod a point. I have a restriction map that goes from the value at CP mod CP to the value at CP mod E. The value at CP mod E, I had an action of CP on this. And the fact that here I had a unique map down to a point that told me that this part actually factored through the fixed points. So here I have the CP mod E, the CP fixed points, and the restriction actually landed inside there. So co-induction of M, I would have, if you gave me just now a set, the co-induced one took the CP-fold Cartesian power of M. So I want to think of this as a CP thing that just maps from CP into M. And then the value at CP mod CP is just M again. And the map here is the diagonal. And the group acts by permuting the coordinates in the Cartesian power cyclically. This is co-ind of M. If instead I did induction, then here I got CP cross M, and here I got empty set. So these are in general kind of different. I mean, not always. M could be the empty set. But in the interesting cases, these are going to be different. So when I talk about instead things like G-Commutative Monoids, what I want to do is I want to now take this functor that I've written down, and actually I'll do a little more. I can build out of these an endofunctor. So I can take and induce back up the restriction. And this actually has a really nice, formula to write it down. This is just, you take M and you evaluate it on G mod H cross T. So here I have, I get for any M, a couple of kinds of diagrams. The same setup as I had before. Now fin G iso into coefficient systems, where I'm going to take a finite G set and I'm going to send it to M of S cross something. And the coefficient system, it came with this sort of contravariant functoriality. So there's two things that I get for free. First of all, notice that this took the disjoint union. That went to M of S0 disjoint union S1 cross something. Well, the Cartesian product distributes over disjoint union. So this is actually naturally M of S0 cross that something crossed with M of S1 cross that something. So this is giving me a product preserving functor, again, just as we had before. And I could also use the fact that the coefficient system I'm sort of feeding in the things that coefficient systems take as input. And so I could have used the contravariant functoriality and extended there too. And I will in a minute. But for now, let's think of what it would mean to extend this over fin G. So an extension over fin G is what? Well, let me build up inductively. So here's going to be my prototypical example. It's again going to be CP. Well, I have a couple of kinds of maps that I'd want to consider. I have the map point disjoint union point goes to point. And when I think about what that's going to do on this side of the diagram, well, I use this product preserving nature, and this says that that even I could have started with a coefficient system of sets like I was doing here, and I get that M of t is a commutative monoid for all t, and my restriction maps, if I had S goes to T, then the restriction from M of T to M of S is a map of commutative monoids. Sorry, non-unital. This one gives me the unit. And then the other maps that show up, well, for CP, there's only one other interesting kind of map, and that's the one that goes CP to a point. And so this gives me something different. So here, I'm going to have M of CP cross something back to M of something. And again, I've already drawn out sort of what the pieces look like. So here I have M of CP mod E. I have M of CP mod E, and then the maps from CP into this. Here I have M of CP mod E. And I have M of CP mod CP. So this is the data that I want to have. And I had my vowel group action. So if I don't ask for any compatibility, then this is just what it is. It's like I get to sort of choose this arbitrarily. But I don't want to do that. I want to add some compatibility conditions. And the compatibility conditions that I want is, I want to say, well, if I forget all of the equivariants, then I'm looking at the very first case I talked about, namely finite sets. And like CP, when I forget all the equivariants, is just the p element set. And I know what's supposed to happen there. I'm supposed to use my ordinary addition. So here, I'm going to use the fact that in commutative monoids, which I know already M is guaranteed to be a commutative monoid for each of the values. So in commutative monoids, I do have that the Cartesian product is actually the coproduct in commutative monoids. So this in commutative monoids is also the coproduct of a bunch of copies of M. And there's a natural map. Just add these all up. And so when I think about what this is, so maybe if I write it out, I take a function here I sum up, didn't get my sum space. I sum up over G, G times f of M, f of G. And then that actually makes the equivariance work. This was the diagonal. And so I see that whatever goes here, it's a map from the value at the underlying into the value at CP mod CP that has the composite that if I compose with the restriction, I get the trace. So when I compose these, the restriction composed with T is just of some element M is just the sum over G and CP of G times M. This is the usual formula, and I think Clover probably talked about this in her first talk, which, I don't know, I was on a bus, so I didn't quite make it. It's been a week. So this is sort of the defining feature that I see when I have a Mackey functor. I have a CP Mackey functor is two commutative monoids, the value at CP mod CP, the value at CP mod E, together with a restriction map that goes from CP mod CP to CP mod E. The CP mod E level has an action of CP, and I have a transfer map back. And the only condition that I write down is that if I transfer and then restrict, I get the trace. I sum over the elements. So the resulting condition, so if we add an assumption which I need for the equivariance, so if we ask for compatibility with restriction, to all subgroups, then to give myself an extension to fin G is to give a Mackey functor structure. On M. So I can think of my Mackey functors as a particular kind of additional structure that I add to my coefficient system. Now, now if I tie this in to this, and I actually see that this really nicely reflects what we see in topology. So Siegel showed that if I did all this in spaces, this is why I'd invoked him originally. So if I look in spaces, and instead of asking for product preserving on the nose, I ask for just product preserving up to homotopy, then I get a model of E infinity spaces. And if I do the same thing here, then I have to add Shimokawa's name. I get in G-top with this, I get a model of G infinity spaces. And a few times in Jeremy's talk, people asked him, what do you mean by E infinity? And he said, well, the only one he was using was sort of the combinatorial one, the one that works in any symmetrical infinity category. Part of the data is a notion of an E infinity model. Here, I have more structure, and the more structure is exactly this. The more structure is exactly, I'm able to talk about these extensions over not just finite sets, so I don't know how to just multiply a finite set's worth of elements, I know how to multiply a finite G set's worth of elements. And that's like the defining feature, in some sense, of the genuine story. Okay. I have no idea how long I have, so I don't know why I'm looking to watch. All right, so I can now extend this in several directions, but I want to sort of start with this, because it gives me a lot of ways to sort of say what's going on. And the first way I want to extend is I'll extend multiplicatively. All right, while I'm erasing, I said in words but didn't write down that in Mackey functors, induction is co-induction. And that's true in general here. When I have any kind of setup like this, where I'm looking at some preferred way to map FinG iso in, and then I extend it over all of FinG in a way that's compatible with the restriction, then so in my G-Commutative Monoids, when I use the Cartesian structure, I always get that the product that I had is the categorical coproduct, and the thing that I was writing as co-induction, so I'll continue to write it co-induction, is also left adjoint to the restriction. And so I can think about this in a lot of additional ways. I can think about now saying that my commutative monoids have a kind of tensoring over G sets. So I get tensoring over finite G sets, although passing a colimits, I don't need the finite part, where I'm just going to say that if you give me a finite G set, I'll describe it for in two ways. I'll say that S disjoint union T tensor with some G-commutative monoid M is just going to be take S tensor M and coproduct, which I guess maybe I'll write it as the sum, with T tensor M. And on orbits, it's this composite again. Then what I've used is exactly that this construction gives me a way to make sense of, given any G-commutative monoid M, this is really a functor from finite G sets in, not finite G sets in isomorphisms. So why do I care about that? Well, this tells me I get an extension of my Hom objects from M to some N, which really lived in set, to a coefficient system of sets. And there's kind of a yoga that you start to find yourself increasingly enmeshed in as you're doing equivariant homotopy theory, and that is that G spaces are actually enriched naturally in G spaces. And the enrichment that I'm writing down is exactly this one. So anytime I see a map between sort of various G objects, I should ask, is there a way to actually assemble this into the bigger diagram? And what's the value? I'm saying I have this extension. Well, the value at G mod H is just the maps of H-commutative monoids from the restriction of H of M to the restriction to H of N, which via the co-induction being the left adjoint here is the G-commutative monoid maps from G mod H tensor M back to N. Oh, there's like a countdown clock. How much is that going to cut into the coffee break, though? So how angry will people be? Well, I know how to handle this. I'll stop paying attention to the audience. So here, the covariant functoriality in this coordinate gave me exactly the contravariant functoriality in Hom out of it. The fact that the disjoint union in these became the coproduct was exactly that this is a product-preserving functor from bin G up in. So I get this really nice extension. And again, I wrote this kind of agnostically because it really makes sense in any way I would think of G-commutative monoids anywhere. And I can use this to then build, so I can say I can get simplicial objects. I can get a tensoring of simplicial G-commutative monoids over now simplicial G-sets. And if I use this in just this additive context, so like the one I started in, then what I'm rebuilding is I'm rebuilding Bredon homology. So if I took now, I'm holding my M fixed and viewing it as like a constant simplicial thing, then when I do this tensoring and I tensor with a simplicial G set, I've written down a simplicial Mackey functor. And the homology, I doled con, the homology of that simplicial Mackey functor is exactly the Bredon homology. So here, this gives me Bredon homology. If instead I was working multiplicatively, and yeah, I can probably talk about Timbara functors in a minute. So multiplicatively, then I get I get sort of a Lode type construction. And I'll talk more about this on Friday. But what I want to do in the, so I'll just put a forward reference with a smiley face. So in the last minute, I want to talk about a slight generalization of this that allows me to pretty nicely interpolate between these. And the slight generalization is just what I'm going to call an indexing category. So I needed just to have the compatibility with restriction. So I'm going to say that an indexing category for G is a wide, which means it contains all the objects, pullback stable, finite coproduct complete, subcategory of finite G sets. And so I'll just write this as fin G, and then I'll adorn it with a subscript O. And then O is going to be allowed to vary. So 2 examples. Here's one where I take everything. That works. The other one is sort of at the other extreme. I'm going to take, Fingy, triv. This is going to be all those maps, f from S to T, such that f preserves the isotropy. So remember, the stabilizer of f of some s has to contain the stabilizer of s. That's just a statement about the map is equivariant. So to say that it preserves the isotropy is actually to say that these are always the same. And you can check that what this does is it basically says, I don't allow maps between non-isomorphic orbits. And then I take everything that I get from them. And there's a bunch that interpolate between these. I can play the whole game where instead of asking for an extension over all of Fingy, notice Fingy iso is actually contained in any such thing like this. Fingy iso is the thing that you get where you say, what's the initial thing that's wide and pullback stable? So it's contained in all of these. So I can ask for an extension over not all of Fingy, but over just one of these. And I get sort of things that interpolate between, if I did just this one, I would have gotten coefficient systems again, because there's no condition that I put down on the, I didn't write down any of the transfer maps because those change the isotropy. If I did this one, I got Mackey functors, and so I see sort of a hierarchy between them. And that's the other thing I want to talk about on Friday, how I have these choices that I get to make for how I extend and what sort of additional transfer data or what sort of additional compatibility with maps from G sets do I put in. Okay, I'll stop here.
More questions?
So you said that Fingy iso itself was an example. So what does the indexing set category need to fulfill so that we have like additive structure at least?
That's exactly this part. That's a great question. So the additive structure comes from this. I could have repackaged this. I said finite coproduct complete. That's sort of a nice categorical way to say that it's a symmetric monoidal subcategory for the disjoint union, and it has all the fold maps. So in fact, Fingy iso is also, it has all of the, it's also a symmetric monoidal subcategory, but it doesn't have the fold maps. And the fold maps are exactly what I need to guarantee that I have an addition. And then the other thing that Fingy iso doesn't have is empty set goes to point, or empty set goes to t for any t. That's what I need to guarantee the units again. And so I can ask for even a weaker thing, where, as you're saying, I don't ask for all finite coproducts. Instead, I ask for something like it's a symmetric monoidal subcategory. That's something I'm going to want, just it sort of falls out because all the examples have it. And then I ask, what happens if I have some of the fold maps? And in this case, I get something it's a different kind of direction that I could go. Instead of putting in some transfers, I'm actually making some of the levels additive. In fact, once I know that for like G mod H, if I have the fold map for G mod H, so G mod H disjoint union G mod H back to itself, then for anything that sits above G mod H, I have the fold map because I just pull back. And so I get something where like at below some level, it's commutative monoids. But then I don't ask for anything else. So I get weird things.
Other questions? If not, then thank Mike again.